Now the 10th transformation is how to draw the graph of trigonometric inverse functions. So say for example, I have to draw the graph of y equals arc sin x or sine inverse of x. So in order to draw the graph of sine inverse x, I'll draw the graph of sine x from minus pi by 2 to plus pi by 2 and codomain is from minus 1 to plus 1. So in this interval, this function is both 1, 1 and on 2. It will be defined from minus 1 to plus 1 to minus pi by 2 to plus pi by 2. From minus 1 to plus 1 to minus pi by 2 and plus pi by 2. And I'll write this as y equals sine inverse of x. Now I'll mark these intervals on graph. So I'll mark minus 1, plus 1, and I'll also mark plus pi by 2 and minus pi by 2. Now the method that I'll follow, I'll take up points on the graph of sine x and then I'll interchange x and y. So this point on sine x is pi by 2 comma 1. So if I'll interchange it, I'll get 1 comma pi by 2. So at 1, I'll mark a point which is 1 comma pi by 2. Now this point is 0 comma 0. So if I'll interchange also, I'll again get 0 comma 0. And now this third point, it is minus pi by 2 comma minus 1. So now at minus 1, it will be minus pi by 2. So I have marked 3 points on the corresponding sine inverse graph. Now I'll draw y to x line and then I'll take the reflection of fx about y equals x line. So my graph will be, so this is how we can draw the graph of sine inverse of x. Now for cos inverse x, I'll draw the graph of cos x. Now cos x is defined from 0 to pi to minus 1 to plus 1. Now cos inverse x will be defined from minus 1 to plus 1 to 0 to pi. Now again I'll take points on cos x. So this point is 0 comma 1. So here it will be 1 comma 0. This point is pi by 2 comma 0. So it will be 0 comma pi by 2. And then this point is pi comma minus 1. So now it will be minus 1 comma pi. Now if I take y equals to x line and if I try and take the reflection, my graph will look like. So that is the graph of y equals cos inverse of x. Now in order to draw the graph of tan inverse of x, I'll draw the graph of tan x between minus pi by 2 and plus pi by 2. Now for tan inverse of x, I'll draw x-axis and y-axis. Now in the graph of tan x, there are vertical asymptotes at pi by 2 and minus pi by 2. So for tan inverse of x, I'll draw horizontal asymptotes at minus pi by 2 and plus pi by 2. Now I'll mark corresponding points. So when x is minus pi by 2, y is minus infinite. So that means when x is minus infinite, y will be minus pi by 2. Here this point is when x is 0, y is 0. So at 0, inverse function will also be 0. Now for this point, when x is pi by 2, y is plus infinite. So that is when y is plus infinite, x is plus pi by 2. So that is the graph of tan inverse of x. Now for cot inverse x, I'll draw the graph of cot x. Now for cot inverse x again, I'll draw horizontal asymptotes at 0 and pi. So at 0 and at pi. So when x is 0, y is plus infinite. So at plus infinite, cot inverse x will be 0. So at pi by 2, it's 0. So at 0 it will be pi by 2. And then at pi, it is minus infinite. So at minus infinite, it will be plus pi. So if I'll draw this graph, it will look like. So that is the graph of cot inverse of x. Now for cosec inverse x, I'll draw the graph of cosec x between minus pi by 2 and plus pi by 2. So again, for the graph of cosec inverse of x, I'll mark these points. Shall connect it. So that is the graph of cosec inverse of x. So for secant inverse x, I'll draw the graph of secant x between 0 to pi except pi by 2. Now again for secant inverse of x, I'll draw the axis. I'll mark the points. Now there is a vertical asymptote at pi by 2. So here it will have a horizontal asymptote at pi by 2. Now this point here is 0, 1. So here I'll have a point on 1, 0. Now when x tends to pi by 2, y tends to plus infinite. So that means when x tends to infinite, y tends to pi by 2. So I'll draw this graph. In the same way, when x is pi, y is minus 1. So at minus 1, now it will be pi. And then when x tends to pi by 2, y tends to minus infinite. So at minus infinite, it'll go towards pi by 2. So that is the graph of y equals secant inverse of x. Now let us take a question. Suppose the given question is secant inverse of x whole square minus 6 secant inverse of x plus 8 greater than 0, and I need to solve this inequality. So I can factorize it. So if I'll factorize it, I'll get, so if I'll put it on a number line, so this is 2 and this is 4. Sign of the rightmost is plus, so plus, minus, and then plus. This actually is secant inverse of x. Greater than 0 is positive, so either it is less than 2 or greater than 4. So the condition I'll get is either secant inverse of x is less than 2 or secant inverse of x is greater than 4. Now in order to determine the value of x, what I'll do is I'll draw the graph of secant inverse of x. Secant inverse of x cannot be greater than 4 because its principal value ranges from 0 to pi. So it cannot take a value greater than pi. Now in order to find the interval where secant inverse of x is less than 2, I'll draw a line at y equals 2. Now I need to find the interval where the graph of secant inverse of x lies below the graph of y equals to 2 line. So the graph of secant inverse of x lies below the graph of y equals to 2 line is from minus infinite to secant 2 and then from 1 to infinite. So answer to this question will be y belongs to, so from minus infinite to secant 2, and I'll not include secant 2 because there is no equality in the question. Union, then from 1 to infinite. I'll take another one. The next question is, find the complete set of values of a such that the equation sine inverse of x equal mod of x minus a has at least one solution. So what I'll do is, I'll draw the graph of sine inverse of x. Now I'll also draw the graph of mod x minus a. So there'll be two cases. Case 1, when a is a positive number. Now when a is a positive number, if I'll draw mod x plus a, then I can shift the graph on the right. I'll keep shifting the graph. Now there'll be one point a beyond which there'll be no point of intersection. So the maximum value of a for which this equation will have at least one solution is when mod of x minus a will pass through the point 1, pi by 2. So I'll put the point. So when x is 1, so 1 minus a is equal to pi by 2. 1 minus a equals plus or minus pi by 2. Here the value of a will be 1 plus pi by 2. So the maximum value of a for which it will have a point of intersection is 1 plus pi by 2. Now if I choose this a as a negative number, then I need to shift the graph of mod x on the left. So if I'll move the graph of mod x on the left, then again there'll be a minimum value of a beyond which there'll be no point of intersection. So in that case, again, the graph of mod of x minus a should pass through 1, pi by 2. So again, 1 minus a is equal to pi by 2. So again, I'll get a equals 1 plus or minus pi by 2. Now, because a is a negative number, here the value of a will be 1 minus pi by 2. So the given equation will have at least one solution when the value of a lies between 1 minus pi by 2 to 1 plus pi by 2. Thank you. So the 11th transformation is graph of self-adjusting property in inverse trigonometric function. Now this property is very important not just in inverse trigonometric functions but in entire calculus. Now before discussing how to draw the graph of these functions, let us discuss two things first. Now the first thing is, if a line makes an angle 45 degrees with x-axis, then its slope is 1. And if a line makes an angle 135 degrees with x-axis, then its slope is minus 1. And the second point is, if a line intersects y-axis above origin, then its y-axis intercept is positive. And if a line intersects y-axis below origin, then its y-axis intercept will be negative. Now say for example, suppose I have to write the definition of this part. Since angle is 45 degrees, slope is 1, so I'll simply write x and then now it will intersect y-axis above origin. So that means its y-axis intercept will be plus pi. So its definition will be x plus pi. So now we can start drawing our graphs. So suppose I have to draw the graph of y equals sine inverse of sin x. Now before I can draw this graph, I must know the principal value range of sine inverse functions. So the principal value range of sine inverse function is from minus pi by 2 to plus pi by 2. So what I'll do is, I'll draw the axis. So I'll mark these points both on x-axis and then on y-axis. Now what we know is, when x lies in the principal value range, then the value of sine inverse of sin x will be simply x. So what I'll do is, in this interval, I'll draw this y is equal to x line. Then I'll draw these zigzag structures. So now it will be pi, it will be 3 pi by 2, 2 pi, minus pi, and then minus 3 pi by 2. Now I'll start writing the definitions. Now for this part, it makes an angle 135 degrees. So therefore it will be minus x, and now it will intersect y-axis above origin. So it will be minus x plus pi. Now for 3 pi by 2 to 5 pi by 2, now this is plus x and it will intersect y-axis below origin. So it will be x minus 2 pi. Now again for this, minus 3 pi by 2 and minus pi by 2. So here again it will be minus x, and then because it will intersect below origin, so it will be minus x minus pi. So I can write sine inverse of sin x as x when x lies between minus pi by 2 and plus pi by 2. Between pi by 2 and 3 pi by 2, I can write it as minus x plus pi. Between 3 pi by 2 and 5 pi by 2, it will be x minus 2 pi. And between minus 3 pi by 2 and minus pi by 2, it will be minus x minus pi. All I need to do is, I need to know its principal value range, and in that range, I'll need to draw the graph of y is equal to x line, and then I'll need to create those zigzag structures. Now in the same way, I can draw the graph of cos inverse of cos x. Now for cos inverse, principal value ranges from 0 to pi. So I'll mark this interval. In the principal value range, it will be x. So I'll draw y is equal to x line. Now again, I'll draw these zigzag lines and then I'll mark the point. So this is pi, 2 pi, 3 pi, minus pi and minus 2 pi. Now between minus 2 pi and minus pi, it will be plus x and then plus 2 pi. Between minus pi and 0, it will be minus x plus 0. Between pi and 2 pi, it will be minus x plus 2 pi. And then between 2 pi and 3 pi, it will be x minus 2 pi. So that is the graph of cos inverse of cos x. Now we'll move on to tan inverse of tan x. Now for tan inverse x, the principal value ranges from minus pi by 2 to plus pi by 2. So I'll mark this interval on x-axis and y-axis. Now in this given interval, tan inverse of tan x will simply be x. So I'll draw y is equal to x line. And because minus pi by 2 and plus pi by 2, they are not included. So I'll draw open circle there. Now in the case of tan inverse and cot inverse, there is a small difference vis-a-vis sine inverse and cos inverse. In the case of sine and cos inverse, we used to draw zigzag lines. Now in the case of tan inverse and cot inverse, we will simply draw parallel lines. So that is the graph of tan inverse of tan x. I can write the definitions also. So in the same way, I can draw the graph of cot inverse of cot x. Now for cot inverse x, principal value ranges from 0 to pi. So I'll mark this interval on x-axis and y-axis, and then it will be y is equal to x line, and then again I'll draw parallel lines, and I can write definitions also. So that is the graph of cot inverse of cot x. So for cosec inverse of cosec x and secant inverse of secant x, I'll use the graph of sin inverse of sin x and cos inverse of cos x respectively. And there is a small difference in the principal range of sin inverse and cosec inverse. In the same way, there is a small difference in the range of cos inverse and secant inverse of x. So I'll just need to keep that difference in mind. Otherwise, I can use the same graph. So I'll take up an example. Say for example, suppose I have to find number of solution of the equation cos inverse of cos x equals 10 minus x upon 10 when x belongs to 0 to 10. So what I'll do is I'll draw the graph of cos inverse of cos x. So principal value range of cos x is 0 to pi. So I'll draw this line, y is equal to x line, and then 2 pi, 3 pi, and then 4 pi. So this is pi, 2 pi, 3 pi, and just after 3 pi it will be 10. Now I'll also draw this straight line, which is y equals 10 minus x upon 10. So when x is 0, y is 1, and when x is 10, y is 0. So I'll draw this line. In the given interval, when x belongs to 0 to 10, these two graphs, they intersect at 3 distinct points. So therefore, the number of solution of this equation is 3. Thank you.
Now we'll prove formulas for multiple angles. We'll need to find the formula for sin inverse 2x into under root of 1 minus x square. Now we'll take this expression as y. So it will be sin inverse 2x into under root of 1 minus x square. Now this formula, it looks like 2 sin theta into cos theta. So what we'll do is we'll let x as sin theta or theta is sin inverse of x. And we know that principal value range of sin inverse of x is from minus pi by 2 to plus pi by 2. Now we'll put x as sin theta. We'll get this y as sin inverse 2 sin theta into cos theta. So it will be simply sin 2 theta. Now 2 theta, it will lie in the interval from minus pi to plus pi, which is not principal value range of sin inverse. So we simply cannot cancel sin inverse with sin. So what we'll do is we'll draw the graph of sin inverse of sin x. That is the graph of sin inverse of sin x. This is minus pi. This is minus pi by 2. It is pi by 2 and it is pi. Now between minus pi by 2 and plus pi by 2, this is x. Between minus pi and minus pi by 2, it is minus x minus pi, and between pi by 2 and pi, it is minus x plus pi. Now in this interval from minus pi to plus pi, there is a change of definition at minus pi by 2 and there is a change of definition at plus pi by 2. So here we have to consider three separate cases. So we can write y equals, now this first interval when 2 theta lies between minus pi and minus pi by 2. So 2 theta, it lies between minus pi and minus pi by 2. Now in this interval definition is minus x minus pi. Now here x is 2 theta. So we'll get this as minus 2 theta minus pi. Now in the second interval, which is principal value range for sine inverse. So when 2 theta lies between minus pi by 2 and plus pi by 2, it is simply x. So we can cancel sine inverse with sine. We'll get 2 theta. And this third interval, when 2 theta is greater than pi by 2, but less than or equal to pi, here definition is pi minus x. So it will be minus 2 theta plus pi. Now we'll replace theta with sine inverse of x. So we can write y equals minus 2 sine inverse of x minus pi when minus pi is less than equal to 2 sine inverse x is less than pi by 2. It will be 2 sine inverse of x when 2 sine inverse of x lies between minus pi by 2 and plus pi by 2, and it will be minus 2 sine inverse of x plus pi when 2 sine inverse of x is greater than pi by 2 but less than equal to pi. Now we'll try and simplify this in terms of x. So what we'll do is we'll divide everything with 2. So we'll get minus pi by 2 is less than equal to sine inverse x is less than minus pi by 4. Now we'll take sine both sides. Now sine minus pi by 2 is minus 1 and this is x, and sine minus pi by 4 is minus 1 by root 2. So if x lies between minus 1 and minus 1 by root 2, then this expression is equal to minus 2 sine inverse x minus pi. Now here if we'll divide by 2, we'll get minus pi by 4 is less than equal to sine inverse x is less than equal to pi by 4. Now we'll take sine, we'll get minus 1 by root 2 is less than equal to x and is less than equal to 1 by root 2. So if x lies between minus 1 by root 2 and plus 1 by root 2, in that case we'll get this result as 2 sine inverse of x, and then here it will be pi by 4 and pi by 2. So pi by 4 is 1 by root 2 and pi by 2 is 1. So if x lies between 1 by root 2 and 1, then in that case this formula will be minus 2 sine inverse of x plus pi. Now this y is sine inverse 2x into under root of 1 minus x square. Now we'll rearrange this formula, then we can simply write 2 sine inverse of x. It will be, now for this first part, we'll take this sine inverse here, so it will be minus pi minus sine inverse 2x into under root of 1 minus x square when x lies between minus 1 and minus 1 by root 2. Now for the second part, 2 sine inverse x, it is equal to sine inverse 2x under root 1 minus x square. So it will be simply sine inverse 2x into under root of 1 minus x square when x lies between minus 1 by root 2 and plus 1 by root 2. And this third one is when x lies between 1 by root 2 and 1. So here, if we'll take this 2 sine inverse x on the left hand side, then we'll get pi minus sine inverse 2x into under root of 1 minus x square. So this is the formula for 2 sine inverse of x. Now here the question is the least integral value of k for which this inequality is true for all x belongs to R.
Now here first we need to find the value of sin inverse of sin 12 and cos inverse of cos 12. Now we'll draw the graph of sin inverse of sin x. So this is pi, 2 pi, 3 pi and 4 pi. Now 12 will lie somewhere here. Now this definition is x minus 4 pi. So sin inverse of sin 12 will be simply 12 minus 4 pi. Now we'll draw the graph of cos inverse of cos x. So this is 0, pi, 2 pi, 3 pi and 4 pi. Now 12 will lie here. Now this definition is minus x plus 4 pi. So cos inverse of cos 12 will be minus 12 plus 4 pi. Now if we'll add them, everything will cancel. So this is nothing but 0. So this right hand side is nothing but 0. So we get our question that we need to find least integral value of k, for which k minus 2x square plus 8x plus k plus 4, it is greater than 0 for all x belongs to R. Now it is a quadratic expression. A quadratic expression is always positive when a is greater than 0 and d is less than 0. Now if we look at a is greater than 0, then the condition is k minus 2 is greater than 0 and value of k is greater than 2. And the second condition, that the value of d is less than 0. Now d in this case is 64 minus 4, k minus 2, k plus 4, it is less than 0. Now we'll divide it by 4. So it will be 16 minus k square plus 2k minus 8 will be less than 0, or we can write this as k square plus 2k minus 8 minus 16, it is greater than 0, which is k square plus 2k minus 24 is greater than 0. Now we'll write this as k plus 6, k minus 4, it will be greater than 0. So this is minus 6 and this is 4, plus minus and plus. Here the value of k is either greater than 4 or the value of k is greater than 6. But we already know that k is greater than 2. So the condition that we'll get from here is value of k should be greater than 4. Now the least integral value of k for which this inequality always holds is k equals 5, and that's your option D. Now another question is, we need to find number of integral solutions of this equation sin inverse of sin x equals cos inverse of cos x in the interval 0 to 5 pi. So what we'll do is we'll draw the graph of sin inverse of sin x. So this is 0, pi by 2, pi by 2, minus pi by 2, pi, 2 pi, 3 pi, 4 pi and 5 pi. So we'll draw this graph. So that is the graph of y equals sin inverse of sin x. Now we'll draw the graph of y equals cos inverse of cos x. So here we'll need to draw graph from 0 to pi. So this is 0 and this is pi. So it will be this straight line x and then this value, this straight line, and then this value, this straight line, and this value. So that is the graph of cos inverse of cos x. Now these two graphs, they intersect in x belongs to 0 to pi by 2, both included, union 2 pi 2. Now this is 2 pi plus pi by 2 and L be 5 pi by 2, union
4 pi to 4 pi plus pi by 2, and that is 9 pi by 2. Now in this interval, when x lies between 0 and pi by 2 is 1.54, we'll have two integral values, 0 and 1. Now between 2 pi and 5 pi by 2. Now 2 pi is nearly 6.28 and 5 pi by 2 is 7.85. So in this interval, there is only one value, which is 7, and 4 pi is 12.56 and this is 14.13. So here we'll have 13 and 14. So number of integral solutions in this interval should be 5 and no option matches with it. So answer to this question should have been 5 solutions from 0 to 5 pi. If we take not inclusive 0 to 5 pi, then in that case answer will be 4. Now here the question is, draw the graph of fx equals sine inverse of mod sin x plus cos inverse of cos x. Find the range of the function. Find the points of non-differentiability. Also find the value of this integral from 0 to 10 pi sine inverse of mod sin x plus cos inverse of cos x dx. Now we are given this function fx, which is sine inverse of mod sin x plus cos inverse of cos x. Now period for this function is pi and fundamental period for this second function is 2 pi. So this function fx, it is periodic with the period 2 pi. Now what we'll do is, we'll write the definition of fx between 0 to 2 pi, we'll draw its graph and then we'll generalize the function. Now we'll recall the graph of sine inverse of mod sin x. We know that this graph is from 0 to pi by 2 x, from pi by 2 to pi it is minus x plus pi, from pi to 3 pi by 2 it is x minus pi, and then from 3 pi by 2 to 2 pi it is minus x plus 2 pi. So this is the graph of y equals sine inverse of mod sin x. Now we'll draw the graph of cos inverse of cos x. It's a very standard function. So this is 0, pi and 2 pi. Now between 0 to pi it is x, and between pi to 2 pi it is minus x plus 2 pi. Now we'll write definitions for this function fx. Now first definition is when x lies between 0 to pi by 2. Between 0 to pi by 2, both the definitions, they are x. So it will be simply 2x. From pi by 2 to pi, here the definition is minus x plus pi, and here it is plus x. So we'll add them, we'll get this as pi. Between pi and 3 pi by 2, definition here is x minus pi, and here the definition is minus x plus 2 pi. So we'll add them, we'll again end up getting this value as pi, and then between 3 pi by 2 and 2 pi, this is minus x plus 2 pi, and it is also minus x plus 2 pi. So it will be 4 pi minus 2x. So we can write this function fx as 2x when x lies between 0 and pi by 2. It will be pi between pi by 2 and 3 pi by 2, and then we have 4 pi minus 2x when x lies between 3 pi by 2 and 2 pi. Now we'll draw the graph of fx. We'll draw the axis. Then we'll mark the points on axis. So this is pi by 2, pi, 3 pi by 2 and 2 pi. Here also let it be pi by 2 and let it be pi. Now first is y equals 2x. When x is 0, it is 0, and when x is pi by 2, it is pi. So we'll draw this graph. Now between pi by 2 and 3 pi by 2, this value is pi. Now between 3 pi by 2 and 2 pi, if we'll put x as 3 pi by 2, we'll get this as pi. And we'll put x as 2 pi, we'll get this result as 0. So between 3 pi by 2 and 2 pi, it will be simply this straight line. So that is the graph of this function fx, which is sine inverse of mod sin x plus cos inverse of cos x. Now this graph will repeat in the same fashion. So this is how we can draw the graph of sine inverse of mod sin x and cos inverse of cos x. Now as you can see, this function is continuous in x belongs to R, but it is not differentiable at pi by 2, 3 pi by 2, 0, 2 pi. So it is not differentiable at odd multiple of pi by 2 and at 2n pi. So it is not differentiable at x equals 2n pi and 2n plus 1 pi by 2. Now we need to find range of this function also. So range of this function is from 0 to pi. As we can see, this graph, it lies entirely in this interval from 0 to pi. So the range of this function, it is from 0 to pi. Now we need to find the value of this integral from 0 to 10 pi fx dx. Now since this function is periodic with a period 2 pi and 10 pi is a multiple of 2 pi, we can simply write this as 5 into 0 to 2 pi fx dx, and this integral from 0 to 2 pi fx dx is nothing but area under this trapezium. So we can simply write this as 5 and then 1 by 2. Now sum of lengths of parallel sides. Now this is 2 pi and this is 3 pi by 2 minus pi by 2, which is simply pi, and then this height, which is also pi. So this area, it will be 5 by 2 into 3 pi square. So it will be 15 pi square by 2. So value of this integral will be 15 pi square by 2. In this video, we'll be discussing graphs of sine inverse of mod sin x and cos inverse of mod cos x, and we'll also discuss some questions related to it. Now, when we look at this function, which is y equals sine inverse of mod sin x, we know that this function will be periodic with period pi, because period of mod sin x is pi. So what we'll do is we'll draw the graph of sine inverse of mod sin x in 0 to pi, and then we'll repeat the graph for all other intervals. So what we'll do is we'll take our interval from minus pi by 2 to plus pi by 2. Now first case, when x lies between 0 to pi by 2. Now in 0 to pi by 2, sin x is positive, so mod sin x will be simply sin x. So we can simply write this as y equals sine inverse of sin x, and in principal value range, sine inverse of sin x is nothing but it is x. So from 0 to pi by 2, this graph is simply y equals x. Now in the second interval, when x lies between minus pi by 2 to 0, in this interval, sin x is negative. So therefore we'll need to write mod sin x is minus sin x. So we'll write sin inverse of minus sin x, and sin inverse of minus x is minus sin inverse of sin x. Now x still lies in principal value range. So here it will be simply minus x. So we'll draw this graph, then from 0 to pi by 2, it is plus x, and from minus pi by 2 to 0, it is minus x. So all we need to do is we'll just need to repeat this graph to get the graph of sine inverse of mod sin x. So that is the graph of sine inverse of mod sin x, and this is pi, 2 pi, minus pi and minus 2 pi, and we also know how to write definitions for different parts. Now for this part between pi by 2 and pi, here the definition will be minus x plus pi, here it will be x minus pi, here will be minus x plus 2 pi, this one is going to be x plus pi, here it will be minus x minus pi. So this is how we can draw the graph of sine inverse of mod sin x, and we can also write definition of sine inverse of mod. Now we look at the graph of sin x and mod sin x, then from 0 to pi, both the graphs they're same. So in 0 to pi, graph of sine inverse of sin x will be same. So another way of drawing the same graph can be from 0 to pi, draw this graph and then repeat the graph. So again, we'll end up getting the same graph. So this is how we draw the graph of sine inverse of sin x. Now we look at the graph of y equals cos inverse of mod cos x. Now again, cos inverse of mod cos x, it will have fundamental period of pi. Now we look at the graph of cos x. And mod cos x, the graph of mod cos x and cos x is same between minus pi by 2 and plus pi by 2, which is an interval of length pi. In this interval, graph of cos inverse of mod cos x will be same as graph of cos inverse of cos x. Now, if we look at the graph of cos inverse of cos x, then this graph, it will be x from 0 to pi by 2 and it will be minus x from 0 to minus pi by 2. Now again, we'll repeat the same graph. And this is the graph of y equals cos inverse of mod cos x. So as you can see, graph of sine inverse of mod sin x is same as graph of cos inverse of mod cos x, and their definitions are also same. So this is how we draw the graph of sine inverse of mod sin x and cos inverse of mod cos x. Now let us take some problems. Find the range of the function square root of mod of sine inverse of mod sin x minus cos inverse of mod cos x. Now we'll recall the graph of sine inverse of mod sin x and cos inverse of mod cos x. This is the graph for y equals sine inverse of mod sin x, and since sine inverse of sin x is greater than or equal to 0, then graph of mod of sine inverse of mod sin x will be same as graph of sine inverse of mod sin x. Now we have also studied that graph of cos inverse of cos x is same as graph of sine inverse of sin x. So we can write this function fx as square root of sine inverse of mod sin x minus cos inverse of mod cos x, and since both these functions, they have the same definition, they are same function. So this is simply 0. So this function, it is a constant function and its value is 0. So range of this function is simply 0. Now here the question is, if sine inverse mod cos x minus cos inverse mod sin x equals lambda has at least one solution, then lambda belongs to which of the following intervals? Now we can write sine inverse of mod cos x as pi by 2 minus cos inverse of mod cos x, and in the same way we can write cos inverse of mod sin x as pi by 2 minus sin inverse of mod sin x. Now we'll replace these two definitions, then we can simply write this as sin inverse of mod sin x minus cos inverse of mod cos x, and it should be lambda. Now we know that definitions of sin inverse of mod sin x and cos inverse of mod cos x, they are exactly same. So both these functions, they'll have the same value at all the points. So value of this function is simply 0. So the only possible value of lambda if this equation has a solution is 0, because this function, it is a constant function whose value is always 0. So answer to this question is this option A. Now question number 10, it says, recall that sin inverse t, which is arc sin t, is a function with domain -1 to +1 and range -pi by 2 to +pi by 2. Now it says, consider the function fx, which is sin inverse of sin x, and then we'll need to find whether these three statements, they are true or false. So what we'll do is, in this question, we'll draw the graph of sin inverse of sin x. So we have already discussed the graph of sin inverse of sin x in one of the previous videos when we were discussing graphs. So I'll put the link to that video in the description below. So we'll draw the axis. And then for sin inverse, principal value range is -pi by 2 and +pi by 2. So we'll draw -pi by 2 and +pi by 2 on both the axes. Now between -pi by 2 and +pi by 2, it will simply be x. And then we'll keep drawing these zigzag lines. So that is the graph of sin inverse of sin x. Now the first question is, the function fx is well defined for all real numbers x. The domain of this function is simply x belongs to R. So that means this function is well defined for all real numbers x. So which is true. Now the second is, the function fx is continuous wherever it is defined. So this function, it is continuous for all x belongs to R. So this is also true. Function fx is differentiable wherever it is continuous. So at these points, we know that we have two different tangents. So that means this function, it is continuous for x belongs to R, but it is not differentiable odd multiples of pi by 2. So that means third statement is simply false. So answer to this question is true, true, and false. Now let us take another example, and which is, if the area enclosed by the curves fx equals cos inverse of cos x and gx equals sin inverse of cos x when x belongs to 9 pi by 4 to 15 pi by 4 is a pi square upon b, then we need to find the value of a minus b. Now this function cos inverse of cos x, it is a standard function, and we know how to draw the graph of cos inverse of cos x. So we'll draw this graph. So this is 0 to pi, 2 pi, 3 pi, 4 pi. So this is 0, pi, 2 pi, 3 pi and 4 pi, and here this value is pi. Now this function cos inverse of cos x, it is a periodic function with fundamental period 2 pi. Now we'll draw the graph of sin inverse of cos x. Now we know that sin inverse x is pi by 2 minus cos inverse x. So we can write this is pi by 2 minus cos inverse of cos x. So basically graph of gx is pi by 2 minus cos inverse of cos x. So we'll draw the graph of gx. Now here our basic graph is cos inverse of cos x. First we'll draw the graph of y equals minus cos inverse of cos x. So it will be this graph 0, pi, 2 pi, 3 pi, 4 pi, and here this value will be minus pi, and then we'll take the transformation y minus pi by 2 equals
minus cos inverse of cos x. Now y minus pi by 2 means we have to shift this entire graph pi by 2 units along positive y-axis. Now we shift this graph pi by 2 units along positive y-axis. We'll get this graph as this. So this is 0. It'll be pi by 2. This is pi, 2 pi, and here it will be pi by 2 and minus pi by 2. So that is the graph of sine inverse of cos x. So we'll draw the graph of sine inverse of cos x. So this is pi by 2 and this is minus pi by 2. This is pi by 2, pi, 3 pi by 2 and 2 pi. That is the graph of y equals sine inverse of cos x. Now this is minus pi by 2 and this is plus pi by 2. Now this function again, it is a periodic function with the period 2 pi. Now we need to find area between these two graphs in the interval 9 pi by 4 to 15 pi by 4. Now we can actually write 9 pi by 4 as 2 pi plus pi by 4, and we can write 15 pi by 4 as 2 pi plus 7 pi by 4. Now since both the functions, they are periodic with the period 2 pi, so what we'll actually do is, rather than solving this function from 9 pi by 4 to 15 pi by 4, we'll find this area from pi by 4 to 7 pi by 4, which is from this point pi by 4, and 7 pi by 4 is 2 pi minus pi by 4, so which is this point. So we'll need to find this area. Now this point here is 7 pi by 4. This again is pi by 4. This value is pi. So this height is pi minus pi by 4, which is 3 pi by 4. And here this height, it will be pi by 2 plus pi by 4, which again is 3 pi by 4. So this required area, it will be 1 by 2 and then length of the base. Length of the base is 7 pi by 4 minus pi by 4, which is 6 pi by 4, that is 3 pi by 2 into this height, which is 3 pi by 4 and plus half. Now again length is 3 pi by 2 and height again is 3 pi by 4. So this area, it will be 9 pi square by 8. So comparing with the given value of A is 9 and value of B is 8, then the value of A minus B is simply 1, and that is the answer to this question.